All right, here we are back looking at electric forces. And this was a problem that we finished up with, or we were looking at the end of the last lecture. So let's go ahead and start from this. We're looking at the electric force. That's how you pronounce that. I guess it's Coulomb's law, but we said that the electric force is a preferred, for myself, a preferred way of expressing this. So it's the electric force, and see, they call it electric force too. Electric force using vector components, and we had 3 charges, and we got a chance to go back and do vector addition. And I think all of you, right, were pretty enthusiastic about that. So what we said was, in a force diagram like this, what we can do is we can isolate one charge at a time and look to see what the net force would be on any of the individual objects in our force diagram. And fortunately, they did not ask us to do all 3. They just picked one of these out, charge number 3, and specifically asked about what the net force would be acting on charge 3. Well, there was a force from charge 2, which pushed it in this direction, but there was also a force from charge 1, which pulls it, attracted it in this direction, and we had to go in and do the vector addition. And what we came up with was that the net effect of both of those forces were having an effect specifically on charge 3 with a vertical component and a horizontal component. We solved for that magnitude, and we solved for the angle. So moving on, kind of a follow-up question to this. Again, this is the electric force. They asked, this is kind of an interesting question. Let's imagine that we take a 4th charge that's negative, and it has a force or a charge of 50 microcoulombs, and it's a negative charge. Where could we put that so that charge 3 now would have no net force at all? All the forces would balance out on charge number 3. And so what this diagram is showing here is, in the previous example, we had included the forces from objects 1 and 2 and determined the net force was at, oh look, they got the same number we did, right? 65 degrees, pretty good. 282 newtons. And so what we want to do with our negative charge is place it here, with the idea that the negative charge placed here will create an additional force off in this direction on charge 3. So charge 3 now is going to experience a force due to this newly placed charge, and we want to place it at a distance. See, we're going to figure out what the distance is right here. We're going to place it at a distance where the forces will exactly balance out. So that's what the force diagram looks like, what we have here. And then here we are doing the calculation. So we've got a force of 282 newtons. We want to create a force over here of 282 newtons. And we want to match the angle exactly. So the angle we've already solved for. We want it at an angle of 64.6 degrees, but back in the other direction. So 64.6 measured this way. And then we can go in and write down the electric force equation and solve for distance. So I put in the charges, I put in the force constant, I put in the 280, that's 282. It looks like 2.82, but it's 282 newtons. And the distance we came up with, distance I ended up with, you guys always check these. If you find any errors in my calculations, let me know right away, and I will get those corrected and reposted. But I ended up with a distance of 0.282 meters, or 28.2 centimeters. Is that a reliable number? And looking back at some of these other diagrams, I'm thinking, yeah, it's kind of, 28 centimeters is kind of like these other numbers. This is 30 centimeters and this was 6. So yeah, I'm expecting something kind of the same order of magnitude, and ended up with 28.2 centimeters. All right. Now, kind of a funny thing with human consciousness and pattern looking, looking for patterns and things, this always throws me off. So there was a 282 here, and I got a 282 here for an answer, and I'm thinking, oh my gosh, is there some kind of is something going on here? And I think not. I think it's just kind of a coincidence here, right? This is even taking a square root. So that's going to happen from time to time, I guess. Anyway, kind of an interesting coincidence. All right, so we've looked now at electric charge. We have looked at electric force, and now we're going to look at electric field. Now let's think back about this. What were the gravitational analogs to this? When we were looking at gravity, we looked at gravitational charge, which is mass. So for the gravitational force, the property that we look at in an object is its mass. And then we looked at gravitational forces, and we looked at gravitational fields. So we did kind of the same thing. Now, I don't think this diagram is especially useful, but let's see if we can try and say something about it. Whenever we have an object with charge, so here is a charge located at some point. At every location surrounding that charge, we can define what's called an electric field. And saying that it's the force divided by a small charge, I don't know if that's useful or not. If it's useful, fine, but let me take a shot at it this way. That charge has an influence on all of its surroundings. Now, when we say it has an influence on the surroundings, it means that when I place a charge at some location, what happens if another charge wanders by? Another charge comes by. Well, if another charge comes by, this charge is going to feel an effect. Now, even before this charge comes by, what we can say is this charge already by itself has created an electric field. Everywhere around it, there is this field that it's generated, and when another charge comes through, the field has an effect on it. So that's kind of interesting. Rather than saying the two charges directly affect each other, what we say instead is that each charge creates a field, an electric field, and another charge coming through that region will feel the effects of the field. Now you might be thinking, well, you can kind of solve things either way. You can do a direct force calculation, or you can talk about an electric field, and that's true. Why do we bother introducing an electric field? Well, think of the gravitational field. You know, the gravitational field of the Earth at the surface, we determined to be 9.80 newtons per kilogram. Now, once we've defined the electric field, little g, we don't have to go back and recalculate it every problem. So now that we know what the gravitational field is, we can just work directly in terms of the field. So one reason for introducing this idea of a field is for convenience. There's also a conceptual reason driving this. So it turns out that forces do not propagate immediately. Forces do not have an immediate effect on charges, do not have an immediate effect on other charges. It takes time for the force to propagate. And we use the field as a way to understand that delay that takes place. So if I have a charge here, it generates an electric field. When I move the charge, the field changes, but not instantaneously. If I move the charge to a new location, the regions away from the charge, it takes time until a region out here knows that the charge has moved. And so we use the electric field, and we use gravitational fields also, as a way of keeping track of if the charge moves to a different location, how long will it take until the field adjusts to that change that took place in the charge. So there's a delay effect. If I have a charge here and another charge comes through, this charge immediately feels the effect at the location in the electric field where it's passing. It doesn't immediately feel the effect of the other charge itself. Here's a charge. Maybe you guys have heard this analogy or this example. What would happen if the sun, holding the Earth in orbit through a gravitational effect, what if the sun suddenly disappeared? What would happen to the Earth's orbital motion? And Earth's orbital motion would continue for 8 minutes. So Earth, even if the sun disappeared, Earth would continue to follow its orbit for 8 minutes as if the sun were still there. And then it would head off in a straight line. Now, why 8 minutes? And that's because, given the distance between the sun and the Earth, it takes 8 minutes for the field, the gravitational field of the sun, to propagate its effect out to where the Earth is located. So again, Earth would not feel the effect that, if the sun is currently there, we're guaranteed that for the next 8 minutes we'll feel the gravitational effects. So who knows? Maybe the sun's disappeared, we just don't know about it. We wouldn't know about it for 8 minutes. Now, the speed at which gravitational fields propagate, the speed at which electric fields and magnetic fields propagate, is the speed of light. And you're thinking, well, that's kind of a coincidence. Why is everything propagating at the speed of light? And it doesn't have to do with light. It has to do with how space and time are put together. So again, this is another advertisement for Physics 4C, I guess. In Physics 4C, we'll look at special relativity and we'll learn about the mathematical connections between space, distances measured, spatial distances versus time. In any case, for our practical purposes, the speed of light is so fast, these fields propagate so quickly, that to a very good approximation we can treat them as if the forces are instantaneous. But just to let you guys know, kind of an interesting story to tell about these fields is that the presence of a field means that it takes time for the fields to adjust for changes in the placement of the charge. If the charge gets up and moves, the field is going to take some time until the field effect appears from that. All right, so all that stuff said, here's a charge, and this diagram is representing if we pick kind of random locations surrounding the charge, there is a way to go in and calculate what the effect would be, what the electric field effect would be at each location. Here's another attempt. I don't know if this diagram is any better. Here's a charge, and they have drawn in electric field lines. Here is a point right there, and it's saying that we can go in and calculate what the electric field would be at that location. Okay, here's maybe a couple better diagrams. So for a point charge, for a positive charge or a negative charge, we define an electric field. Now, the official field, the electric field, it's a vector quantity. Electric fields have direction, as do gravitational fields. So again, we can do this analogy with gravity. With the gravitational field, it wasn't that difficult because gravity is always attractive, and we just defined the gravitational field as pointing downwards towards the center of the planet, or if it's if it's a star or a galaxy or something, we can kind of determine what direction the gravitational field would be in. With plus and minus charges, we kind of have to flip a coin and ask ourselves, do we want the field directed away from the charge or towards the charge? And the convention we work from is that the electric field surrounding a positive charge is directed away from the charge. With the negative charge, the electric field is directed towards the charge. Now, what's hard to avoid here is that these directions do not mean anything is moving. Okay, so those arrows don't represent motion, they represent a direction of the electric field. Now, we talked about electric fields take time to propagate. These arrows are not talking about propagation. So there's nothing leaving a positive charge and there's nothing arriving at a negative charge. It just happens to be, well here, let's think of it this way. So if another positive charge wanders by, the electric field has been defined in a way where if here comes, a positive charge wandering by, it will feel a force in the direction of the electric field. If a positive charge, again, the positive charges are the way we treat those as the default. So the default here is, if a positive charge comes by, what direction would the force be if it's a negative charge? And the direction of the E field is defined in the direction that a force would be oriented if a positive charge came by. So that's what the direction means. So again, the electric fields, they're vector fields. And I hope in your calculus classes, you guys see this in Math 3B, 3C? In any case, if you haven't seen it, it's fine, because we're going to discuss it here. And then when you take your math classes, you can tell the professor that you've already seen this in your physics classes. But a vector field means that at every location in space, there is a magnitude of the electric field and there's a direction of orientation. Another way to represent a vector would be to represent its components. So you can think of this at every location in space, like point A right there. There is an EX component, there's an EY component, and an EZ component. Now, for point A that we've got there, to me right now, if we use a standard coordinate system, it looks like there's an X component and there's a Y component and there's not a Z component. And the X and Y components are kind of the same, and the overall direction is, roughly at 45 degrees. So that's what a vector field refers to. Okay, and this field is called the electric field. We'll see more fields show up. We're not through with fields. Okay, so let's try that. Let's practice this newly introduced concept of an electric field. So we're going to be looking at the electric field surrounding a single point charge, and that's what we've defined right here. Now, what they're saying here is, in these diagrams they've got here, you really have to cover up part B. Don't get confused because there's a lot of stuff going on. So cover up all of part B and just look at part A. So when I do that, what it's asking is, if I cover this up, all I have is one charge. And that charge that object has an amount of charge that's 3 microcoulombs, and it's a negative charge. So I can put a little minus sign there, and the magnitude again is 3 microcoulombs. Well, what they're claiming over here is something with a negative charge at point P would have an electric field direction oriented back towards the charge. Now, another issue with these vectors is kind of counterintuitive, or when we draw a vector like this, we have to remind ourselves that the length of the vector only applies to one point. It only applies to point P. None of these other points out here are being represented by that vector. The electric field we're talking about is just the field at point P. Because when we replace the negative charge with, okay, now I got to cover these up. Now we're going to replace this with a positive charge, same magnitude of charge, but it's positive instead of negative. Then at that same location in space, the only effect is to reverse the vector directions. So again, these two vectors are referring to the strength of the electric field at one point, and it's that point right there. Now they're claiming that when we do the calculations, it's going to be 300,000 newtons per coulomb. Those are going to be the units for our electric field. Let's see where that comes from. So here is example 21.6. Here is my solution to that. Now, here's the picture that we drew on those previous slides. Here is the charge Q. Here is point A. Okay, when we talk about points, I like using capital A. I hope you guys don't mind. But I'm going to call it point A, and then if there's another point, I'll call it point B. I always think of going from point A to point B. I don't think so much of going from point P to point Q. But anyway, be ready for that. That's probably what my diagrams are going to show. Now, here's point A, and since the charge is positive, the electric field at that point is going to depend on the fact that it's positive. It'll be directed away. The magnitude of the electric field is kq over r squared. Now, if you're thinking that looks kind of like the force equation, or the force formula, you're right. So the electric field portion of that is kq over r squared, and what that says is, in order to calculate the force, we just have to multiply by the amount of charge on the second object. So we'll get to that and see some examples. So right now, the electric force, due to that one charge, right, we're not saying there needs to be another charge right now. One charge by itself has an influence on its surroundings. It has this field that responds to the presence of that charge. Its magnitude for a point charge will be kq over distance squared. Now, what is this? And this is a handy way to keep track of orientation of the field. I'm going to claim it's a handy way. It's what's called a unit vector. Now, we've seen unit vectors before. Back in Physics 4a, we used unit vectors ijk. The unit vector I was in the x direction, and the unit vector j was in the y, and the unit vector k was in the z direction. So now what I'm going to do is I'm going to define a radial unit vector, and the radial unit vector points away from the object. So you can think of it this way. When I place the object here and I'm using this unit vector, what I can imagine is that there's a coordinate system centered on the object. And so the r direction would be pointing away, directly away from that object. And what the unit vector does is it enables me to separate out magnitude from direction. So the idea is this. If I have a point charge, it's going to have an electric field at every location in space. The magnitude of the electric field is always going to be kq over r squared, every time. Magnitude is going to be kq over r squared. Going back to what we said earlier, if the charge is in motion, that changes, but we're not going to be looking at examples where the charges are moving so fast that we have to alter the formula. So we're going to use this low speed approximation and say that the field is always going to be given, the magnitude is always going to be given by kq over r squared. So that just depends on distance. Now, if I want to figure out the orientation, then I can add on the unit vector. Okay, and that's the idea. So what that enables me to do is I don't have to worry about direction and magnitude at the same time. I'm just going to go in and calculate magnitude. So kq over r squared, I plugged in the k, I plugged in the q, there's just one q instead of two, and that means when I do the units now, instead of newtons, it's going to be newtons per coulomb, and sure enough, when I did the calculation, I got their answer. Now, what you're finding here is this 8.99, 10 to the 9th. That can actually be rounded a bit. Now, I put the 8.99 in, but you could also, if you're taking a midterm, just put in 9 times 10 to the 9th. Try it both ways and see what difference it is, because let's face it, if I put in 9 times 10 to the 9th, that's only an error I've introduced of 1 part in 899. Now, 1 part in 899, that's like 1 part in 900 or 1 part in 1,000. That's going to create like a 0.1% difference in my answer. So to 3 sig figs, that will hardly ever show up. Almost never. So anyway, just a bit of a shortcut that you're welcome to use. And again, try it either way and see how that works. But the E field magnitude, the electric field, which I'm going to be calling that an E field for short. So an E field magnitude is 300,000 newtons per coulomb. So that says when another charge comes by, and let's say, for example, the other charge has 1 coulomb of charge, that force is going to be 300,000 newtons for every coulomb of charge. Now, we've seen that a coulomb of charge is a lot, but that's the magnitude. Now, what happens when I switch from a positive to a negative charge, but I keep the same distance, and I keep the same charge? I don't have to go back and redo the calculations. I just use the very same number, but in my diagram, I reverse the direction of the arrow. So I'm letting the diagrams keep track of direction. When somebody tells you the number is positive or negative, what that person now has to do is figure out, I wonder what coordinate system they're working in terms of. And sometimes that's hard. It's easier, and it's actually more secure in terms of communicating and getting things, being on the same page, to draw a diagram and then report the magnitude. So that's certainly my preferred format if you're taking an exam, for example. The examples that we look at in lecture, almost always it's going to come down to calculating a magnitude and then using a diagram to show which direction that applies to. All right, I hope all this helps. It takes some practice. Everything else in physics, it's practice, rehearse. Had a student from years ago, went on to UC Berkeley in electrical engineering, and she became a very established electrical engineer. And that was her favorite saying was, rehearse. You have to go through the problems, and you have to think about them. So if the idea is, if I do this problem enough times, I'll just kind of naturally begin to know what numbers to put in. That's not true. It doesn't work that way. You have to go through the problem and think about what you're doing and talk to yourself, or talk to other people if you're working with other people on the problems. Talk to other people that you're working with, but you really need to think about what each step means. And that's where you build up the conceptual intuition about how to set up a problem. When you encounter a new problem, you can say, oh, I know what principles apply. I'm going to be able to set it up this way. So practice these problems, talk to yourself, tell yourself what's going on, not in terms of plugging numbers in, but conceptually why. Why am I doing this step? It's because it's representing these forces that are happening in nature. This electric force, it's representing how the electric force works. Did we say it all? I think we did. Okay, I'm going to move on here. So let's take a look at this next item. All right, now that we've looked at electric fields due to individual point charges, we are ready to move on, which always happens, right? Now we're ready to take 2 charges and look at the combined electric field effect from 2 separate charges. So what we've got here now is I have a charge over here, it's negative, and I have a charge over here and it's positive. And I want to take a look at this location right there, a certain distance from charge 1, a certain distance from charge 2, and I want to find out what the combined electric field effect will be due to the presence of both of those charges? Well, at point P, charge 1 has an electric field directed back towards charge 1 because it's a negative charge. So the electric field due to charge 1 looking at point P is going to be directed back towards charge 1. Charge 2, on the other hand, is positively charged. Its electric field will be directed away from charge 2. So what's happening is, at point P, both the electric field effects are in the same direction. They're going to reinforce each other. What we've done now with this diagram, I didn't get my calculator out, I didn't plug any numbers into any formulas, I just drew the diagram and I've already established what direction the E field will be in. Okay, and so there's a lot of stuff we can take care of in the diagrams up front, and that's always a good approach, is start thinking about what's actually going on in the problem. Rather than pulling out some formulas and plugging some numbers in right away, let's conceptually get a diagram like this set up. This counts for a lot on a midterm problem. So let's say that you get this much set up and you establish the directions and you say something like the E field will be in this direction. That might get you, half the points right there without ever using a formula. So this part of the course is really, really important, and so conceptually setting up the problems counts for a lot on the midterms. Okay, all the numbers are here. Let's see. So there's two parts to the problem before we go to the next. Before we start solving it, the numbers. One last thing. Let's see, part A says find the electric field, and we did that. Part B says that now that I've got these two charges, now these two charges are going to be placed somewhere, and we're thinking of it as if these two charges are locked into place. So they're fixed. They're creating a certain environment, and now what we're going to do is we're going to bring an electron into that E field. So again, I'm thinking of Q1 and Q2 locked into place. An electron is now placed at that location, and then I let go. If I let go of an electron starting from rest, right at that location, tell me about its motion. And what will happen is that the electron will be repelled by charge 1. The electron will be attracted by charge 2. So that electron will have forces acting on it. Electrons are negative. So the forces acting on the electrons will be exactly opposite to the electric field. So that's how forces and fields are going to be related here. If it's a positive charge, if it's a proton, let's place a proton right at that location and let go. If I let go of a proton, the forces will be to the left. If I place an electron there, the forces will be to the right. So, and they'll be the same amount of force because protons and electrons have the same amount of charge. So again, there's a lot of these things with electric and magnetic forces. It's either this way or that. Depending on is it positive or negative, that just reverses the effect. So let's go ahead and we've got the distances, we got the charges. Let's take a look at the solution here. Okay, point P became point A. Okay, thank you, I appreciate your patience with that. Q1 and Q2, now I made a big deal of putting a minus sign here and a plus sign here because that's what I need. And we've already established from the diagram that both E1 and E2 will be directed to the left. So to calculate the net field, I'm going to calculate E1 and E2 magnitudes and just add them together. So for the E field formula, that's KQ over distance squared. Now the Q1s and Q2s, R1s and R2s are listed. R2 is the distance between charge 2 and the point. R1 is this distance over here. And since I'm just calculating magnitude, the diagrams have already told me what directions we're going to be in. I don't have to put in negative 25. I can just put 25 into my calculator and find out these two numbers. So if you're wondering, why does E1, why is it coming out 5.62? Why is it not negative? It's because I've already taken care of directions with the diagrams. So the magnitude of E1, the magnitude of E2, I add those together. That's what we determined using the charges. And this is the combined electric field effect from the presence of charge 1 and charge 2 together. Now, in part B, we're going to place an electron. That's a symbol for an electron. And one thing that can be confusing is the symbol for the electron looks just like the constant little e, the fundamental charge. So don't get those mixed up. I will put a little negative sign here. So that represents an electron. Place electron at point A. Okay, done. Now, since for the electron, the charge is going to be negative E, but look, when I actually carry out the calculation, I'm ignoring that minus sign. So what I can do now is show that the direction of the force, since the electron's negative, the force will be exactly opposite the field direction. So remember, if it's positive, the force is right in the direction of the field. If it's negative, the force is exactly opposite. So again, I've used the diagram to determine all of the directional information. Now I just have to find out how much force will there be. And for the amount of force, I can use Q times E. So I'm ignoring the vector signs and taking Q, 1.60 10 to the minus 19 coulombs, times the electric field, and I'm getting 1.01 10 to the minus 10 newtons. Now, let's look at just some of the numbers themselves. How big is the electric field? Well, it's like 632 million newtons per coulomb. Million's a really big number. And that's what happens in these problems. It doesn't take much charge to generate an enormous field. And if we trace it back numerically, what that traces back to is our electric force constant, little k. Remember, that was 9 times 10 to the 9th. And so I'm getting this enormous electric field. Now, when I calculate the force is actually tiny, right? It's like 100 piconewtons. It's this tiny, 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 tiny force, but that's because it's acting on just one electron. And even though it's a tiny force, that will have an enormous effect on our electron. That electron is just going to take off. It's going to accelerate at an amazing acceleration. We'll see some examples of calculations with that. But that's, this is a good problem to stop and stare at and kind of think about what's happening in terms of placement of electric charges, what will their electric field be at a given point, and then what effect will that field have on other charges that happen to stop by. In this case, it was an electron that came by. Here we go. I did follow this up with part C. So when I said we're going to see this in future examples, it's on the next page. So we finished the problem that they gave us. Part B, we calculated the force, and it's to the right, and it's 100 piconewtons. Now I wanted to ask, what will the acceleration be for my electron if I let go of it? So I placed the electron there and measured the force, but now I let go, and the acceleration of that electron is going to be force divided by its mass, and the mass of an electron, 9.11 times 10 to the minus 31 kilograms. That calculation says that the electron now of the electron would be 1.1 10 to the 20th meters per second squared. And I hope you guys are cautious enough about numbers that when you get 10 to the 20th in your calculator, you stop and think, I have never, so far in my physics career, physics 4A and now physics 4B, ever seen a number that big. Why is that happening? And it's because the electron has a tiny, tiny mass. And you have to ask yourself, is that a reasonable number? And it turns out it is. It turns out that electrons and protons and such, these little, these really low mass fundamental particles, can have enormous accelerations. Okay. Now, as far as how fast can they start traveling, if this sort of an acceleration is applied to this electron for a very long period of time, it's going to acquire an enormous speed, and that's where we have to take physics 4C. So physics 4, it turns out that there's no such thing as speeds faster than the speed of light. So there's actually a speed limit, and it turns out the formulas we learned in physics 4A don't correctly account for that. So we'll learn a little bit of special relativity in physics 4C, so that when we run into, now the acceleration itself is fine, but we'll deal with this more when we get to physics 4C. So the acceleration numbers, if they're enormous, that's okay. The velocity numbers, if we calculate velocities faster than light speed, it means that we have to go back and use special relativity. I think we're going to be okay with that. I'll try and point to some examples where the speeds are enormous, but still sensible. All right, so, oh no, now it's a two-dimensional example. See, they keep building on this. So now we're getting an electric field, but it's due to charges here and here. But the points we're looking at are point A and point B. Now, point B turns out to be complicated enough. I don't think I did it. I just did point A. So you guys are welcome to go in and calculate point. I should have done both. Let me see. If I remember right, I think I just did the one. Now, let's take a look at point A. So at point A, there's going to be an electric field. And the electric field at point A, notice there's no charge there anymore. It's a location in space, but there's no charge at that location. So the electric field at point A, oh, they're using point A and B, very good, is going to be due to the electric field from charge 2. So charge 2 will have its influence, it's going to have an effect at point A. Charge 1 will also have an effect at point A, and we're going to have to do vector addition again. So the electric field for a negative charge is going to be directed towards that charge. So that arrow pointing towards charge 1 is the electric field at point A due to charge 1. This electric field, directed vertically, is the electric field due to charge 2. Now for charge 2, it's also going to have an effect at point A. And this is due to charge 2, so those are the two E fields, the electric fields we're going to add together. Now we have to do vector addition, which means we have to divide things into components and add the x components together and the y components together. Pythagorean's theorem, so kind of the same thing we did before looking at forces. And here we go. So here is point A, and here is the electric field due to charge 1, here's the electric field due to charge 2. That diagram has taken care of all my directional information. I can now stop worrying about positive and negative charges. All the positive and negative charge information was included once I determined directions of E1 and E2, and now I'm just calculating magnitudes. So KQ1 over R1 squared, I can treat the charges as all being positive, and or just look at the magnitudes. And I'm getting electric field magnitudes now, 1.25, 10 to the 6th million newtons per coulomb, 5 times 10 to the 6 million, so the 10 to the 6 is the million here, newtons per coulomb. And I went through and once again determined my angle. The angle here was 30 degrees. And so I've got a diagram that looks like this. And I've got x and y components for E1, but I only have y components on E2. So once I get E1 and E2 calculated, which we said we did, then when I look in the x direction, the only E field components in the x direction are going to be E1 cosine theta. So I took my E1 multiplied by cosine theta to get my 1.083, 10 to the 6. Now in the y direction, I've got all of E2, but I have a little bit of E1's component. There's a vertical component to that, and it's in the opposite direction. So I'm going to subtract that. So E2 minus E1 sine theta, and that gives me the 4.375. Now, my final diagram here, where I've taken all the x components and all the y components, are given by those numbers. Turns out my y component is much larger than my x component. So I didn't draw this to scale. I drew this more generically. And as far as calculating the strength of that E field, the combined effect, again, I'm going to use Pythagorean's theorem. I'm going to combine the components, square each one, add them together, and take a square root. So that becomes 4.51, 10 to the 6 newtons per coulomb. Tan phi is equal to, so the phi I've defined in here, Ey over Ex, 4.04. I took an inverse tangent of that and got 76 degrees. So again, it's not to scale, it's tipped more vertically than what I have here. But I've determined the magnitude of the electric field at that location, and I've determined its direction. All right, so that's the idea. Again, it's a vector addition. Now, electric force and electric field, there's a relation between those, but they're not the same thing. So read problems carefully. If a problem asks for a force, but you solve for a field, then you've done something wrong. If it asks for a field and you solve for a force, that's a problem. So make sure you're answering the question that you're being asked in the homework or on the midterms or whatever. Make sure that you read the problems carefully. Force and field are not the same thing. Now, I didn't do point B, but let's go back and see how would you guys carry out the calculations for point B. Well, in point B, again, I'm going to have a contribution from charge 1 and a contribution from charge 2. Now, since this is negative and this is positive, I'm going to get the E fields oriented in a way where the net E field is going to line up right along the horizontal direction. Now, why did that happen? Well, it turns out Q1 and Q2 are the very same magnitude. They're 50 microcoulombs. And the distance between Q1 out to point B and Q2 out to point B is the very same distance. It's 40 centimeters. This is forming an isosceles triangle. See how the baselines here are 26 in both cases, and the vertical distance is 30 centimeters. So what that's going to do is it's going to give me the very same magnitude of E field. So the magnitude of E field 2 is going to match the magnitude of E field 1 if I have two fields with the same magnitude tipped at the same angles, opposite directions. Those two vectors are going to combine so that the overall direction of the E field is right along the x-axis. All right, so from the diagram, again, we wouldn't have to put any numbers in here. If we looked at the diagram, recognize that the charges are the same magnitude, the distances are the same, the angles match, we could already say that the net E field is exclusively in the x direction without getting a calculator out. We wouldn't have to calculate any numbers to say that. And that's the kind of intuitive determination that you want to practice developing. You want to develop that to where you can look at problems and start saying things about the problem before you've put a bunch of numbers in. Don't jump to putting a bunch of numbers in formulas. Think about the problems first and see what kind of things you can figure out just working from the diagrams. I should have done the numbers on this. I'll have to go back and see. All right, so here's the advice on calculating these electric fields. It says problems solving in calling them electric forces and electric fields. So draw diagrams, show all the charges with the signs. Now, once you know the signs, you can figure out the electric field and force directions. So once you've drawn the diagrams and identified which charges are positive and which ones are negative, that's enough information that the electric and field and force arrows, the vectors that you're drawing, you can determine what direction they're in. Then calculate the magnitudes of those forces and fields using our formulas. So using the electric force formula and the electric field formula, you can calculate how much force, how much field there will be. Then apply those to the diagram. Go back to the diagram now and see what directions those forces are in and add them as vectors. Carry out vector addition to get your results. Combine the net x effect and the net y effects can be added together to get the overall net force or field and the angle and the direction. And then, check your answer. Go back to the beginning. Once you've got the directions and the magnitudes figured out, go back and look and see if it makes sense. Now, we talked earlier about kind of anticipating what the answers might be, and then once you get your answers, you stop and go, was that kind of what I expected? Or am I getting something that seems contrary to what I was expecting? Okay, that's really important. So start developing that sort of intuition. All right, we are trying to decide if we want to, let's go ahead and get started with this. This is probably going to be where we pick up in the next lecture. As we had mentioned at the beginning of chapter 21, they really stuffed a lot of stuff into chapter 21, kind of this first chapter on electric charge and forces and fields. It kind of feels like it could have been 2 chapters, but in any case, if you feel like there's a lot of stuff here, it's because there is. Don't panic. You're correct. There's a lot of things being introduced. Now that we've calculated what the electric fields look like for a point here and a point here and a point here, now we want to look at what are called continuous charge distributions. Let's take a look. Okay, so here's an example. What if instead of a point charge, what if we had a stick or a rod where charge was placed continuously along that? How can we solve for an electric field at some point, let's say point A, if I've got charge all along here? Well, what we can do is we can take the formula we've been working from. This was the electric field formula due to a point charge, and apply that in a manner where each location along this stick of charge corresponds to a point charge. It's kind of that calculus approach, right? The idea is, hey, any extended object, any continuous object, I could treat as a series of point objects all lined up. So see that point right there? It's got a little bit of charge, and that little bit of charge is generating a little bit of electric field. So I can change the equation for a point charge into, well, the very same equation. But now I'm acknowledging that I'm really only looking at a tiny portion of the charge, and I'll eventually carry out an integral. So I'm going to do an integral calculation along a continuous charge distribution. So coming back to this slide before, a continuous distribution of charge can be treated as a series of infinitesimals, point charges. The total field is the integral of the infinitesimal fields that are due to each bit of charge. So each bit of charge is dq, and each infinitesimal field is dE. Remember that the electric field is a vector. So since what I'm calculating could possibly have components x, y, and z, there's a possibility that we would have to do a separate integral for each component. So this depends on the problem. There are problems where the distribution is simple enough. I don't have to do 3 separate components. I can just do one and you're done. But there's going to be other situations where we have to do more. I don't think we ever have to do 3 components. We're going to look at some examples where we do 2. Well, let's go ahead and take a look at this first example. So let's pull out the electric field formulas. Here is a point charge, there is a point in space, and the electric field at that location, kq over distance squared, times the unit vector, and again the unit vector, the radial unit vector, points away from the charge. Now, instead of a point charge, now what I have is a stick of charge. I have a bunch of point charges all lined up. So I can treat that as a point charge, point charge, point charge, point charge, point charge, point charge, and each one of them will be dq. And then at point A, I can say this point charge is going to generate a little piece of electric field, an infinitesimal piece of electric field. And in this particular case that we've drawn, we are going to have x and y components. So for the particular location in space that I've picked, I'm going to have 2 components. Now, what if I looked at a point here? If I picked a location in space that lines right up with all the charge, then the electric field would only have 1 component. But because we picked a point here, and it wasn't my choice, I think it was the textbook. Oh, it was my choice. Let me take that back. Sorry. Sorry, textbook. I made life more complicated than I needed to. So I picked a point right here to show that I have x and y components, and that as I move from one location on that linear piece of charge, the direction of dE will slowly change. The angle theta, that's a variable. When I carry out the integrations, I have to acknowledge, I have to treat that theta as being a variable. I can't treat it as a constant, because it's not. So you guys know you guys are like integral experts, right, for integration. Math 3B, oh my gosh. There's some difficult problems in Math 3B, right? Setting up integrals and variable substitutions. And so in physics, what happens is we use several of those different sorts of techniques, but I hope what you guys find is once we start using some integration on some of these problems, that once you start doing these, there's kind of a set of classifications of integrals that just keep showing up. We kind of keep coming back to the same setup over and over. So in a math class, in your calculus classes, the integral could be anything, right? Crazy sort of stuff. But in physics, well, like this formula right here, there's an r squared. I mean, it's not going to be r to the 7th or r to the 13th or something like that. It's going to be r squared. Okay, so again, in physics, we're representing things that happen in nature, and for whatever reason, most of the things that happen in nature have a particular pattern to them, and so we keep kind of setting up the same integration over and over. Things change a little bit, but we start to see that it's kind of repetitive. All right, that said, let's take a look. What the heck does this mean? Well, when I write down that the net E field, vector, comes from integrating dq over distance squared times a unit vector, integrating over the unit vector means that as I move from one location to the next, theta is changing. The direction is changing. Now, what I want to do, this is compact form. This is actually how you carry out the calculations. So, and we talked about that, or the slides talked about that back a couple of slides. The way we carry out this calculation is to do one integral for the x components and one integration for the y components. And what I can do is take each of these DEs and say the DEX is going to be combining all the cosine thetas, and DEY is going to be combining all this. So that's what the integrals are actually going to look like. Now we have to develop these some more, and so we'll start doing that. That's probably a good place to end for the day. So we're kind of bumping up against this integration, and I hope you're looking forward to doing some of this. I always feel like, back when I was taking calculus, the calculus was, it's pretty interesting, and you could set up these integrals and carry out calculations based on them. But then I started taking physics classes, and it was like, oh my gosh, this really applies. Math was fun, playing around with these integrations, but in physics, every integral means something. It's actually being applied to some kind of a situation. And so we can see, carrying out the integrations, we can kind of see how nature works. In this case, how do the electric fields and electric forces work? So I'm going to stop there for today, and then we'll pick up with these electric force and electric field integrations next lecture.